Hello, everyone. Welcome back. Today, we want to talk about estimating a population mean. So if you saw my previous video on estimating a population proportion, you'll know it's very similar in concept, although some of the details are different. For our goals, we'll be able to find what's called a critical t-value for a t-distribution for a sample. We'll explain what that means, how we use that. Then be able to construct a confidence interval for a population mean, then also find the minimum sample size we need then to help estimate a population mean. Now, in general, estimating population mean is a lot like estimating a population proportion. So this time we want to call our true population mean is mu, which we don't know. And then we're going to do some to create a sample. And we're going to put sample, we're getting a sample average or sample mean we're going to call X bar. And then we want to use that X bar then to construct a population mean. There's a lot of words here, but I'll kind of summarize it. You can read it on your own. Base of the sample mean is called a point estimate. And so that's how we're trying to estimate the actual population mean. But we don't really know how close that is. So what we want to do then is try and create a confidence interval for using our point estimate, our sample mean, then to kind of estimate what the mean is for the entire population. Now, in realistic cases, in most cases, we're not going to know what the standard deviation of the population is, because after all, the standard deviation is created from the population mean. We don't know the population mean. That's what we're trying to estimate. So the way to handle that is use something called a student t-distribution, which, as we'll see, the details are very much like if we did know the population mean, we just use, instead of using the population standard deviation, we use the sample standard deviation. Let's talk about that. There's something called a student t-distribution. It says if a population has a normal distribution, then the distribution of t instead of z, with X bar, our sample mean, minus the population mean, divided by this new standard deviation where S is actually our sample standard deviation, then divided by the square root of n, which n is our sample size. This is called the student t-distribution, or often just the t-distribution. Now, if we compare that to a standard normal distribution, which we've worked with in the past, then you'll see that looks like this. Okay, so the only difference, as you compare, is here we're using the S, the sample standard deviation, instead of sigma, the population standard deviation, because we don't know the population standard deviation. If we didn't know that somehow, it'd be better to use that. But it's unlikely in most cases we'll know that. Now, this t-distribution is a bell-shaped distribution, but it's wider than a normal distribution since there's more uncertainty in the sample standard deviation. Okay, so let's actually take a look over the right side and actually kind of draw a brief comparison. Let me draw this black line. Let's say this is a standard normal distribution. This is what we've seen before. Okay. Now, right here in the center is 0. That's our mean. And actually, it turns out that's also the mean of our t-distribution. So a few things about the t-distribution. So the t-distribution is different for different sample sizes. And that means it's basically going to be wider or more narrow depending on the sample size, but it's still kind of centered here. And the t-distribution has the same generic symmetric or general symmetric bell shape as a standard normal distribution. It has more variability over smaller sample sizes. And then the t-distribution has a mean t of 0. So basically, if on the same graph, imagine the standard normal distribution. And then if we also drew, and I'll draw this in a different color, I'll actually go over here, pick a different color. And for a similar t-distribution, it would look more like this. So it might be peaked in a similar way, but it's going to be still bell-shaped, but it's going to have what are called wider tails. Okay, it's wider out here because there's more uncertainty. Okay, because we're using the sample standard deviation instead of the population standard deviation or the normal distribution. There's a lot more uncertainty. Okay, so then it has to be wider. So kind of a general rule of statistics is something wider means there's more uncertainty. So that's the case here. So this blue then, once again, is the t distribution. Now, so that's what we're going to use then. So to use this formula, so we need to find, so basically what we're going to have to do is like with determining a population, a sample, or determining creating a confidence interval for a population sample population proportion, we also need to, in this confidence interval, we had to find a critical value. And so we're going to do the same thing here, critical values with the t-distribution. And we'll talk about how to do that because it's slightly different. Now, also, as one more thing about the t-distribution, the sample size gets larger, the t-distribution gets closer to the standard normal distribution. So as the sample size increases, we're getting closer and closer to this standard normal distribution. Now, so let me just read this part. In finding the critical values of the t-distribution, to create a margin of error for a t-distribution, we need to find the critical value t of alpha over 2, similar to z of alpha over 2 to use for creating a confidence interval for a sample proportion for a given confidence level alpha. Since we're using the sample standard deviation S instead of the population standard deviation sigma, we'll have to find what's called the degrees of freedom, for example. Okay, now what this is, it's maybe a little hard to follow, but the main thing to remember is how to find the degrees of freedom. That's the most important. So I'm going to read this again, or as well. The degrees of freedom, or let's call them DF, for a set of sample data is the number of sampled values that can vary after we have fixed one of the values by finding the sample mean. So what that means, we take our sample values and find the sample mean. Essentially, we've fixed one value. And so we only have, in terms of what other numbers can vary, then we have one less number out of one fewer value out of that sample that can actually vary. It says, for example, if we have a sample of size 10 and we set the average of the sample at 90, that's the average we found, then the sum of the samples must be 900. Okay, we can choose any of the values we want for the first 9 samples. Okay, if we choose that, then the last one is fixed by the choice of sample mean. So once again, the idea, if we create a sample of size 10, we're going to say we want the average to be 90, then the sum of the samples, 10 times 90 is 900. And so that means for the first 9 values, we can choose whatever we want. But since we've set this mean to be 90, the last value is already determined then. So what this means for t-distribution, the degrees of freedom is going to be basically our sample size n minus 1. So that's the main point to take away from this. Whatever your sample size is, the degrees of freedom is 1 less than the sample size. So we're talking about how to find critical values. We're going to use a table, which I'll include in the notes, and also then how to use Microsoft Excel to find the same value. So to find the necessary critical value from a t-table, then we'll explain the t-table. We'll use the following procedure. So first, let's take a look for our first examples. To find the critical value or critical t-value for a confidence interval with n equals 31 and a confidence level, 95% confidence level. Okay, so first need to find our degrees of freedom. Let's go back and change this back to black. So our degrees of freedom is going to be 31 minus 1, which is 30. Okay, so with the sample size 31, we have 30 degrees of freedom. Now, our alpha, if we want 95%, then our alpha is going to be 0.05 for 95%. Now, we're going to use this t-table, so let's talk about that. Also, we actually need to a couple more things. So we're going to use what's called the area and the two-tail to find the right value. So in this role, you use the area and two tails. Okay, so this is a t-table, common one. And then what this shows is, let's go with the top. I know it's a little small, but we'll explain this. So you can choose either the area and one tail or area and two tails. We're going to focus on the area and two tails. Now, with this area and two tails, like a z critical value, area and two tails looks like this, where half the area. So for alpha is equal to 5 or 5% or 0.05, alpha divided by 2, we have 2.5% here and 2.5% here. So the critical value is what separates those. I mean, this is a t-distribution, a t-tail. So if actually because of the uncertainty, because a t-distribution has more uncertainty, our corresponding t-value for an alpha of 0.05 will be larger than that of a z-distribution. But if we look, so for 30, so we're going to find under the area of two tails, for degrees of freedom goes to 30, then find the one that matches up to alpha equals 0.05. we look down here at degrees of freedom equals 30. And this other darkened column, these are the most common ones used. That's the reason they're bolded. 0.01 and 0.05 for 30 and 0.05, our value is 2.042. So from the table, T of alpha over 2 is equal to 2.042. Now, let's show how we can do the same thing with Microsoft Excel. So let me actually close the table for a moment. So we have this formula, this function in Microsoft Excel we can use. So t.inv.2t, the two t's for two tails. The inverse means we're essentially doing an inverse. Okay, instead of finding the probability, we're looking for a certain probability to find the area or find the value that separates the area under the curve. So let's go to Excel. And if you notice, once again, what we want to plug in is first the alpha, which is 0.05, and then the degrees of freedom, which is 30. Okay, so let's just squeeze this here. So in Excel, we're going to use t.inv.2t, and then alpha, which is 0.05, and then degrees of freedom, which is 30. Okay, and let's find out what that is. It should be, actually I have a few more significant figures because we'll be using Excel. So if we type that in, so as we'd always do is an equal sign first, then t dot, and here it is, t dot, to make sure you click the right one. Double click on that, then plug in. So the first one is alphas, which is 0.05, and then our degrees of freedom is 30. Okay, hit enter, and you see we get the same thing. So 2.0, 2.04, then 2272. So essentially the same thing. This is rounded to 3 places. Okay, so that's how that works in general. Let's take a look at another example. So here we want to find the critical value for confidence interval of n equals 23 and a 90% confidence interval. So once again, first, let's find our degrees of freedom. So for 23, it's going to be 23 minus 1, which is 22. And alpha this time for 90%, alpha is 0.01. Sorry, 0.1, not 0.01, 0.1. My mistake. So 90%. Okay, so once again, from the table, look at the table first. So for degrees of freedom of 22 and alpha of 1, if you notice, one disadvantage of the table doesn't have all the values, of course. It should have 22. So let's make sure it does. Right, so for 22 degrees of freedom, and here we want the 0.1. Okay, the area under two tails is 0.1. And for 22, go over here, and it's going to be 1.717. And that is our T of alpha over 2. Now, once again, let's look at Excel. All right, so the same formula, t.inv.2t for two tails. Then when click in 0.1, and then degrees of freedom is 22. So let's do that in Excel. Double click on that. So probability is 0.1, and we have 22 degrees of freedom. And we'll see we get, let's get the same thing with more figures, 1.717144. Okay. Do a couple more. Okay, this time, confidence interval, find the critical value for a confidence interval with n equals 7 and 99% confidence. So once again, find our degrees of freedom. So our sample size is 7. So 7 minus 1 is 6. Of course, that's also a very small sample size. Generally, we want to sample larger than that. But if we know it's from a normal distribution, we can do that. There's also something potentially you might not know if you don't know what the mean is. But anyway, and our alpha then for 99% is going to be 0.01. So once again, from the table, value. So this is our degrees of freedom are going to be 6. And we're going to 0.01, so right here. So 3.707. Notice it's a fairly large number because it's in part because of we have a higher confidence level and also have a smaller sample size. So the smaller the sample size, the more uncertainty you have. Also, the more confidence you want, the more uncertainty you have. But anyway, the value is 3.707. And once again, let's do from Excel. And that's going to be t.inv.2t. And that's going to be for 0.01, alpha, and 6. So once again, let's go back to Excel and do that. So type in, make sure you type equals first, then just start typing in. And once you'll be able to find it. Double click on the formula. And then the probability is going to be 0.01. And then we have 6 degrees of freedom. And yeah, so we have the same thing. 3.707428. And once again, that large value, especially compared to the ones we've done before, is because we want a high confidence level and also have a small sample size. All right, one more. Now this is one, well, actually we'll probably just use Excel. All right, so critical value with n equals 170 and a 95% confidence level. So our degrees of freedom is our sample size, which is 170 minus 1, and that's going to be 169. And then 95% confidence level means we have an alpha of 0.05. Now, we're just use Excel this time because, as we'll see, that value, that number is not actually on the table. Now, there's a way you can take care of it when it's not on the table. We'll explain that. In fact, let me just enlarge the table a bit since we don't need the pictures anymore. All right, so if you notice, go down. So it does about the first individual ones up to about 30 or so, then it starts to skip, okay? Now, if you notice, of course, 169 is on here. We have basically between 100 and 200. Now, a couple ways we can do this. Now, it's better to, if you had to choose, the best way to do this was called interpolation. So basically, you essentially interpolate between these two values. That meaning what you do is you essentially use these 2 points. Think of these as 2 points here also. Sorry, this is 0.05. So it's the middle column. So this bolded column here, the middle one. So what you would do is think of these as 2 points on the line, okay? 100 and 1.984, 200 and 1.972, and basically create a straight line with those 2 points, and then you have a formula for a line and plug in degrees of freedom of 1.69. Okay, that's kind of time consuming. Now, if you want to choose the one with a larger, to be more certain, choose the one with the larger value. That's usually the smaller one. Okay, choose degrees of freedom 100, because actually that gives you a larger, to maintain your confidence level, it actually gives you a larger value for T of alpha over 2 to maintain your confidence level. Okay, but the best thing to do here is use Excel, which we can do that easily with 169. Okay, so let's do that. So Excel, once again, so t.inv, and then find the right formula. Double click on it, and then probability is 0.05. And then 169 degrees of freedom. And what we get is 1.9741. Go ahead and write that down, 1.9741, so don't forget it. And then that was, of course, t.inv.2t, and then 0.05, and then 169. Okay, so this is our T of alpha over 2, our critical value. Now, if we compare that, it should be in between the values for 100 and 200, and we'll see that it is, okay? Between 1.984 and 1.972. And it should be a little bit closer, potentially, to this value. I don't want to say a whole lot, because this 169 is way closer to 200. Basically, that's our critical value. Okay, so that's how we do that. That's how we find our critical values. Either you can do the table or Excel. But Excel is probably better since we have a lot more options, especially with larger sample sizes. Okay. Now, next thing I want to talk about then is basically then constructing a confidence interval. And so to do that, we need to find our margin of error. And so for this, here's our margin of error. Okay, so margin of error E is going to be that critical value that we just found, T of alpha over 2, times S, which are sample standard deviation, divided by the square root of N. Okay. Now, and then similar to the way a confidence interval is constructed for population proportion, essentially to find our interval, is we add this value to our, so let's go and start here, subtract this value from our sample mean to find our lower bound, add that value to our sample mean to find our upper bound. And here's basically the procedure below, which we'll find. So essentially the first thing we're going to do is what we just did, is to find our T of alpha over 2, our critical value, and then we'll construct our confidence interval. Okay, so let's take a look at our first example. It says a sample of 35 ACT scores an average score of 27.3 and a standard deviation of 5.8. Construct a 95% confidence interval of the true population average. Okay, so our sample mean is 27.3. Our sample standard deviation S is 5.8. And once again, we don't know our population standard deviation, or else we'd use that. But of course, it's not likely to know that without doing something like this first. Now, so we have alpha is going to be 95%. So our alpha is going to be 0.05. Then our degrees of freedom, I'll just put our N, of course, is 35. So degrees of freedom is 35 minus 1, which is 34. Okay. So first, let's find T of alpha over 2. And here we'll just use Excel again. So it's going to be in Excel, t.inv.2t, and then 0.05, and then 34. Let's plug that in. So 0.05, and then 34. And our value, also probably round this off. Hang on, I must have typed the wrong, sorry, I must have typed the wrong thing in. What did I do? See, I did the wrong thing, just T this, so I wasn't being careful. Always be careful to pick the right formula. In this case, my clue was it was negative. Okay, so once again, type that. So t.inv. Yeah, make sure you click the correct one, which is .2t. Okay, let's try that again. 0.05 and then 34. Yeah, there we go. So let's round and say 3 places, 2.032. Okay. Now, our E is going to be that, so 2.032 times S, which is 5.8, and then divided by the square root of N, the square root of 35. Okay, and actually, let me grab a calculator. And we'll do that. Now, I forgot to grab it before. Okay, 2.032 times 5.8, and then divided by the square root of 35. And that's equal to what I got was, and I'll round this off to say 2 decimal places, though it doesn't say, 1.99. Okay, so that's my margin of error. Now, so my confidence interval, we need an upper bound and a lower bound. So my lower bound is going to be 27.3 minus 1.99. And that's going to be 25.31. And then the upper bound is going to be my sample mean, 27.3, plus my margin of error, 1.99. And that's going to be 29.29. Okay, so my 95% confidence interval, just abbreviate that, is going to be, write it two different ways. So we have 95% confidence that the true mean is between 25.31 and 29.29, or we can write it as just with in an interval notation, so 25.31 and 29.29. Okay, so that's our, so for this sample size, what they're saying is that based on this sample, and if you look, we went through basically went through these steps I mentioned over here in our essentially you found degrees of freedom, okay, found the confidence level, found the critical value, found our margin of error, then we constructed the 1 minus alpha confidence interval. So in this case, 1 minus alpha is 0.95. Okay, and once again, of course, our assumptions, we have a simple random sample, which we do, we assume that otherwise stated, otherwise, and also the distribution must be normally distributed or have a sample size is greater than 30. So that was also true. Okay, let's look at another one. Okay, this says, in a test of weight loss programs, 40 adults use a new weight loss program. After 12 months, their mean weight loss is 2.1 pounds with a standard deviation of 4.8 pounds. Construct a 90% confidence interval estimate of the mean weight loss for the test subjects. Does this weight loss program appear to be effective? So here, not only do we want to do the same thing we did in the previous example, but then also want to try and interpret it in that way. So let's write down what we know. So our N, our sample size is 40 people. Our sample mean turned out to be 2.1 pounds. And our sample standard deviation S turned out to be 4.8 pounds. You can put the pounds if you want or not. Okay. Now, you need to find the other value. So our alpha, since it's 90% confidence, alpha is going to be 0.1. And then our degrees of freedom is going to be our sample size 40 minus 1, which is 39. Okay. Like before, let's find our T of alpha over 2, our critical value. Let's use Excel again. So T dot INV dot 2T. And then remember, first we have our alpha 0.01, and then we have our degrees of freedom 39. Let's do that. So just type T dot 9 to start typing in. Okay, make sure you click on the correct one. And then 0.1, and then 39. And we get 1.684875. So let's do 3 places again. So 1.685. 1.685 for our critical value. All right, so once again, let's construct our confidence interval. First, find our margin of error. And the margin of error is right here. So E, so our critical value, T of alpha over 2 is 1.685 times S, which is 4.8, divided by the square root of 40. But also be careful here, it's the square root of N, not the degrees of freedom. So this time it's 40. Let's find that on the calculator. So 1.685 times 4.8 divided by the square root of 40. And what I get, say, to two decimal places is going to be 1.29. Now, that's going to need to find our confidence interval upper and lower bound. So our lower bound will be the mean, which is 2.1, minus 1.29. .81. And then the upper bound can be found by taking our mean 2.1 and adding our margin of error. So 2.1 plus 1.29 is 3.39. 1.29 is 3.39. Okay. So our 90% confidence interval is going to be 0.81. So we have 90% confidence the true mean is within 0.81 to 3.39. Or if we can also write it as an interval notation is 0.81 to 3.39. Okay. Now, the last question here, the last part is simply to ask, what do we think this means? Okay. So this says, does this weight loss program appear to be effective? So you could say yes, in the sense that basically, so I'll just write over here. So the confidence interval, just abbreviate that, it's normal out of space, is above 0. Okay. So remember, we have 90% confidence that the true weight loss, the mean weight loss, would be somewhere in this interval. Confidence interval is entirely above 0. That means that basically people on average are losing weight. So I'll say is effective. But barely, based on the data. So here is kind of a more subjective view of what do you think it means. So yeah, it looks like on average people are losing weight, but still we're talking about over 12 months, basically average being between, basically our average is only about 2.1 pounds. Okay. And so basically that's not for 12 months, that's not very good. And your probably on body weight could vary by a couple pounds, depending on your overall weight could vary by a couple pounds, in the space of a day, depending on what's going on in your life. So that's probably in a system here, and the way we're thinking about this, yeah, you could say, okay, this technically it's probably effective, but at the same time, real life probably wouldn't be that effective. Okay, let's go back and talk about our last topic, which is, what just happened? I apologize. I don't know what. Hmm. Sorry, I don't know what I just did. Give me a moment here. I'm gonna have to go back and see if I can how to undo what I just did. Give me a moment. Huh. Okay, I'm not sure what's going on. All right, be patient with me here. This is kind of weird. All right, let me try this. Okay. Now, I don't know what happened. Somehow I erased the work that I did. Let me go back and redo that. So let me. So once again, just be patient with me. This has never happened before. So let's see if I can. All right. I can copy this and then put it back over here. Okay. I think that was very bizarre. All right, I may just have to leave it like that. So hopefully you saw that. Okay, that's better. Like I said, this is very strange. Never happened to me before doing this. There we go. Okay. Well, I'm almost back to where I was, so let's hope this will work. Okay. Now, and let me get rid of it over here. Okay, so I think we're there. All right. So our last topic then is finding minimum sample size. I had another example here considered, but I think we'll just go into that. Okay, because the other one's very similar. All right. Now, the same way if you saw my video with finding a confidence interval for a sample proportion, we also want to find like a minimum sample size. We'll do the same thing here. Okay, so for a mean. All right, so here's our formula. And here, one thing is a bit different is actually we're using the z of alpha over 2, not the t of alpha over 2. Okay, and then we're also using the population sigma. So this is just a way of doing, if you actually know what your population standard deviation is, which in most cases you wouldn't, but this, if you do know that, we can actually use the population standard deviation sigma. Okay. Once again, where z is a z-score, like we had with the, when finding the confidence interval for a population proportion. Okay. Now, also, it says the population standard deviation is not available. We can use what's called the range rule of thumb. So this is taking the range of your data values and dividing by 4. So if you have data values, you don't know that, this can often give you kind of a good estimate. You know, obviously not great because we don't know actually what sigma is, but kind of give you a good way of doing that, or at least a way to estimate it. Okay. So let's look at this last one. Assume we want to estimate the IQ, the mean IQ score for a population of statistics students. How many statistics students must be randomly selected for IQ tests if we want to have a 95% confidence interval that the sample mean is within 3 IQ points of the population mean? Okay. Now, let's say what we need. So here we need to know our, here it says use sigma equals 15. So that's what we have. So our sigma is going to be 15. Okay. Now our margin of error E, we also need that. And it says we're going to be within 3 IQ points. So that's going to be 3. All right. And what else we need is z of alpha over 2. Now, there are ways to find this. You can also find this on Excel, but what we're going to do is, in this case, it's so z of alpha over 2 for, actually, let me back up and see what alpha is. So we want 95% confidence. So 95% confidence, we want an alpha of 0.05. Now, our z of alpha over 2 for 95% confidence, we use a small table here because these are the most common ones. Confidence levels 90%, 95%, and 99%. So we want to pick for 95%, or z of alpha over 2 is 1.96. Okay, we're going to plug those in. And so n is going to be 1.96 times sigma, which is 15, then divided by E, which is 3, and then we're going to square this. So once again, use your calculator. And what we get is going to be 96.04. Okay. Now, what we want to do then, but is we want to round up. So for this, so for minimum sample sizes, always round up. Okay. So minimum sample sizes always round up. And so then our minimum sample size will be equal to 97. Okay, you always want to round up because you want to make sure you have more, since you have more confidence. And so the way to achieve that is having a slightly larger sample size, always round up. Okay, let's actually do one more thing on this one. Let's say we didn't know what sigma was, which in most cases we wouldn't. So let's say we want to use, let's say that if let's say we didn't know sigma, but we basically know our data range, okay? So let's say for an IQ, now once again, this would be kind of an estimate, but let's say we knew the data range. Let's just say we had a range from, let's say 50 to 150. Now also, this might have to be based on maybe some of data from the past or previous surveys, because also you wouldn't really know your data range until you actually create the data. And the goal here is to find a minimum sample size. Let's say maybe other people have done similar studies, maybe larger samples, and found the data range usually being like 50 to 150. Okay. Now, so from that, then our sigma, so using this range rule of thumb, use this range rule of thumb, sigma then would be a range, which is going to be based on the range of 150 minus 50. Here I should probably say 2 instead of minus, just to make it clear. I'm not subtracting here. So 50 to 150. So 150 minus 50, or 100, over 4 is 25. Okay, let's see how that changes things. Let's take a look at our formula. Okay, so we had before at 15, now we're going to do 25. So that's actually going to give us require a larger sample size because we're increasing sigma. Okay, but let's plug that in and see. So now our minimum sample size is going to be 1.96. Everything stays the same except for sigma, which is now 25 divided by 3 squared. So let's do that. Right, actually quite a bit larger, okay? So that's going to be 266.78, or once again, if we round up. That's going to be 267. So that's quite a bit larger, okay? And because our sigma was much larger, then that meant that this is much larger. Okay, so it's actually just changing, in this case, just changing our sigma, our standard deviation by 10, actually create a much larger sample size. So that's why, so once again, this range rule of thumb can be useful, but as you see, though, it's not ideal, because in this case, if this was accurate, then we'd have to have a much larger sample, which would take more time and more money to actually find. Okay, so what we learned today then is that how to find a confidence interval for a population mean using a sample. And we use that using the student t-distribution because in most cases, realistic cases, we're not going to know our population standard deviation ahead of time. Thank you. Have a good day.